Imagine a researcher studying how a protein flexes. They start with a sequence, build a contact graph, run a normal mode analysis, and fit a model to predict crystallographic flexibility. Then they hit a wall. A hinged two-domain protein behaves nothing like the compact globular ones the model was trained on. They have two choices: adjust coefficients within the existing model, or admit something new into the vocabulary itself. Perhaps that local softness only matters when it lines up with a global collective motion. That second move, where the very space of allowable scientific objects changes, is what this paper formalizes as discovery. Everything else, however sophisticated, is search. This distinction matters enormously for how we build agentic artificial intelligence, AI systems for science. Today's AI scientists, whether they're calling tools, running simulations, or proposing hypotheses, are extraordinarily fluent at recombining ideas inside a fixed scientific vocabulary. But the moments that genuinely advance science often require enlarging that vocabulary, introducing a new variable, a new operation, a new verifier. The authors, Fiona Wang and Markus Buehler at Massachusetts Institute of Technology, argue that without a principled way to distinguish search from discovery, we can't properly design verifiers, audit provenance, or even measure progress. Existing approaches like scientific knowledge graphs, workflow provenance systems, and categorical accounts of deep learning each capture pieces of this puzzle, but none give a unified semantics that handles both fixed regime iteration and the moment when the regime itself must change. Their framework is built on category theory, which is essentially the mathematics of how typed things compose. Think of it as giving a precise grammar to the engineering structures scientists already use intuitively. A schema is a category whose objects are artifact types, like sequences, contact graphs, or symbolic models, and whose morphisms are allowed operations like building a contact graph from a structure or fitting a symbolic expression. The current state of a discovery system, all the artifacts it has produced so far, is captured by what's called a coprechef, which is just a rule that assigns to each artifact type the actual set of artifacts inhabiting it in a way that respects the operations. The realized provenance graph, every artifact and how it was made, falls out automatically as something called the category of elements. Now, here's where it gets interesting. A fixed regime update, the system adding more artifacts within the existing vocabulary, is modeled as an endofunctor on these states. But this only earns the name endofunctor when the implementation preserves refinement structure, meaning stable artifact identifiers, appendee-only semantics, no silent merging of distinct artifacts. It's an audit contract, not a slogan. Discovery, by contrast, is modeled as a verified regime transition, a functor from the old schema to a new, enlarged one. The old evidence is carried into the new vocabulary using a construction called left con extension, which you can think of as the least presumptuous way to reinterpret old artifacts in the new language. Crucially, if the new regime introduces a type that isn't connected to any old type, can extension assigns it the empty set. Transport alone cannot populate genuinely new content. The residual, what's in the post-transition state but outside the image of transported evidence, is exactly the new scientific content the discovery move added. This gives a precise, non-subjective measure of how much discovery actually happened. The authors demonstrate this with two case studies. The first is Builder-Breaker, a protein mechanics system. The breaker selects proteins designed to stress the current model. The builder proposes edits to a symbolic-directed acyclic graph that predicts within-chain flexibility from contact network compliance and normal modes. A minimum description. Length gate accepts a revision only if it compresses the accumulated evidence better after paired refitting, paying for any added model complexity in bits. Across 4 iterations, the system encounters compact proteins, then terminal flexibility cases, then hinge domain motion proteins like open and closed adenylate kinase, and finally a mixed validation set. The final accepted law is beautiful in its compactness. Predicted normalized B factor equals a constant plus, a coefficient times log compliance multiplied by a thresholded slow mode participation. In words, a residue is flexible when it is both locally soft and participates in the dominant collective deformation. Local softness alone is not enough. Slow mode participation alone is not enough. The interaction is the discovery. What makes this categorically interesting is the post hoc can transport audit. The features log-normalized compliance and thresholded mode amplitude are generator reachable from old physics quantities, just unairy transformations. But mode-conditioned compliance, the product of these two, is only composite reachable. It requires the new regime to admit a multi-input morphism, combining them. The discovery isn't the existence of compliance or normal modes, both of which were always present. It's the admission of a new interaction type, and the gate accepts it with a 54.3-bit gain. The R-squared values are non-monotonic across iterations, going from 0.48 to 0.68 to 0.54 to 0.41, but this is the right behavior. The evidence set is widening to include harder stress tests at each stage. Monotone R-squared would reward chasing heterogeneous data with ad hoc terms. The minimum description length gate, instead, rewards structural parsimony. And indeed, only 25 of 388 proposed edits across the whole run survive, with removals being a high-yield operator. The second case study is CategoryScienceClaw, a categorical layer built on top of an existing agentic platform called ScienceClaw, which already supports type skills, immutable artifacts with parent lineage, pressure-ranked open needs, and workflow mutation, combined with a discourse layer called Infinite for public posts, claim links, and feedback. The categorical layer lifts all of this into explicit objects, morphisms, typed holes, and proof certificates. The worked mechanics example studies a fiber network, deciding whether mechanical response is better captured by a scalar fiber count descriptor or by an orientation tensor anisotropic stiffness surrogate. An Akaike information criterion gate with a delta of 123.87 favoring the anisotropic model accepts the richer description. The rejected isotropic descriptor remains a first-class object in the provenance graph, so model selection itself becomes auditable typed provenance, not just a footnote. Now for limitations. The endofunctorial story is an aspirational specification more than a current reality. The authors are careful to note that ScienceClaw is only weakly categorical in software, lacking enforced schema signatures and explicit refinement maps. The can transport audit in the builder-breaker case is post hoc, performed after the run rather than driving acceptance decisions. Multi-parent artifact synthesis is better modeled as a typed multi-category than as a plain category, which complicates the clean can extension story. And the open problems the authors list are substantial. How do you learn the base schema category from corpora rather than engineering it by hand? What do scaling laws for discovery rate even look like? When does iterating across growing regimes converge productively rather than oscillate? The framework is genuinely useful as a design specification and as a lens for understanding what existing systems do and don't preserve, but turning it into a fully verified executable discovery substrate is future work. Looking forward, the most powerful idea here may be that discovery cost can be operationalized as residual content beyond functorial transport. That gives us a non-subjective handle on what makes one agentic AI system more scientifically generative than another, beyond benchmark performance on fixed tasks. It also reframes the role of physics-based reasoning in machine learning. Rather than AI being an external optimizer bolted onto mechanics, mechanics supplies disciplined concepts, state, load, failure, invariance, constitutive closure, that can shape how self-revising AI systems are built. Now let's walk through some questions you might have after hearing all of this. First, why does the distinction between generator reachable and composite reachable matter so much? Because it tells you whether a new concept is just a relabeling of existing physics or a genuinely new compositional commitment. If a new type is generator reachable, it's an unairy transformation of something you already had, like taking a log or applying a threshold. The mode-conditioned compliance result is striking precisely because it's only composite reachable. The product operation combining local softness and collective mode participation had to be admitted as a new morphism. Without that, the slow mode and the compliance can sit side by side in your schema forever, without ever interacting, and you would never discover the interaction law. Second, why use minimum description length as the gate rather than something like predictive accuracy on a held-out set? Because the evidence set is changing across iterations. The breaker is deliberately introducing harder cases, so predictive accuracy on a fixed benchmark is the wrong target. It would reward adding terms to chase the new data. Minimum description length asks the structural question: does the revised model compress the now larger evidence better after paying for its own complexity? That's exactly the criterion you want when you're trying to grow a model in response to genuine anomalies rather than overfit to whatever just arrived. Third, what's the practical difference between a Copra sheaf and just a typed database of artifacts? The Copra sheaf carries the operations along with the artifacts. It's not just that you have sequences and contact graphs sitting in tables. It's that every operation in your schema, like build contact graph from structure, comes with an actual function mapping the artifacts of one type to artifacts of another, in a way that composes consistently. This composition is what lets you reason about whether a new state genuinely extends an old one or quietly contradicts it, and it's what makes the con extension construction work when you transition to a new schema. For large-scale recommendation systems serving hundreds of millions of users, the most actionable idea here is the separation between fixed regime updates and verified regime transitions. Production recommender stacks constantly add features, retrain models, and tweak ranking objectives, but they rarely distinguish between updates that stay within an existing representational vocabulary and updates that genuinely enlarge it, such as introducing a new entity type, a new interaction modality like short-form video alongside articles, or a new verifier like a long-term retention signal alongside click-through. Treating these as structurally different operations, with explicit transport of old user embeddings and item catalogs into the new regime plus a measurable residual, would give recommendation teams a principled way to audit which launches actually expand the system's capacity versus which are just rearrangements. More concretely, the minimum description length gate idea translates well to candidate retrieval and ranking model selection, where teams routinely face the question of whether a richer model justifies its added serving cost and complexity. Paired refitting on accumulated counterfactual evidence, combined with retraction as a first-class operator, could discipline the tendency to monotonically add features and submodels. And the typed provenance view, where rejected models, failed experiments, and superseded embeddings remain inspectable artifacts rather than being deleted, maps naturally onto the audit and reproducibility needs of large recommendation platforms, where understanding why a ranking decision was made years ago is increasingly a regulatory as well as engineering concern.